Most students lose 4 to 5 marks in mole concept because of one mistake. That is due to lack of clarity in basic important terms of mole concept. After this video, you will be comfortable and confident in important terms of mole concept. Remember students, these important terms are most important for solving numericals in mole concept. Let us start without any delay. Important term number 1, that is atomic number. It is most familiar term, most commonly used term in all calculations. Atomic number is equal to, or which is defined as number of protons, which is equal to number of protons, which we represent by using letter Z. Another term, that is mass number. Mass number we represent by using, or it is equal to number of protons plus neutrons, which is represented by using A. By using these two terms, we can define one important term, that is isotopes. Isotopes are referred as atoms of same element having same atomic number, that is Z, and different mass number, which is A. Remember, atomic number is equal to number of protons represented by Z. Mass number is equal to number of protons plus neutrons represented by letter A. By using these two, we can define isotopes. Isotopes are those atoms of same element having same atomic number, different mass number. For understanding, if you see example for isotopes, we represent 1H1, 1H2 and 1H3. What we call, for example, here 1H1 if I take, the superscript indicating mass number, subscript indicating atomic number. Here all are having same atomic number but different mass number. So first we call it as protium. The one with 2 mass number we call it as deuterium. The one with 3 mass number we refer it as tritium. Among these isotopes, this one we refer it as radioactive isotope. Among 3 isotopes of hydrogen, the radioactive isotope is tritium. So overall, isotopes are those elements or atoms of those elements having same atomic number, different mass number. Best known example, isotopes of hydrogen, protium, deuterium and tritium. So with these terms, if you move further, the most important term for this mole concept, that is the term mole. Very important, the term mole. So how we define mole in terms of chemistry here? First of all, mole is a counting unit. Mole is a counting unit. Where we use mole? For example, in day-to-day life, we refer 1 dozen is equal to 12 units. We know 1 dozen is equal to 12 units. Similarly, here 1 mole is equal to, you can represent like 6.022 into 10 power 23 particles. 6.022 into 10 power 23 particles. First of all, mole is a counting unit. How we use in day-to-day life, 1 dozen is equal to 12 units. In similar way, 1 mole is equal to 6.022 into 10 power 23 particles. But where we use, we can't say 1 mole bananas, 1 mole apples. 1 mole we use only for representing minute particles involved in chemistry like atoms, electrons, protons, neutrons, ions, molecules, etc. For representing these minute particles, we use this special term, that is mole. Number is very big. 1 mole is equal to 6.022 into 10 power 23 particles, representing very big number. So where we use here 1 mole, let us see here. For example, if I write 1 mole nitrogen atoms, 1 mole nitrogen atoms meaning here 6.022 into 10 power 23 nitrogen atoms. Same we can use even for nitrogen molecules. If I write 1 mole N2 molecules, like for example here 1 mole, if I write 1 mole N2 molecules is equal to 6.022 into 10 power 23 N2 molecules. So you can write in any way, 1 mole of O2 molecules, 1 mole of oxygen atoms. So 1 mole meaning 6.022 into 10 power 23 particles. So overall it is counting unit, especially used for counting minute particles like atoms, electrons, protons, neutrons, etc. Then moving to another important term, that is AMU. AMU. AMU meaning here atomic mass unit. Atomic mass unit. So here AMU representing, what is AMU here? It is equal to 1/12 of, it is equal to 1/12 of mass of an atom of carbon 12 isotope. Means if we divide the carbon 12 isotope into 12 parts, the 12th part, if we divide into 12 parts, so each part, that you can say 1/12 of mass of an atom of carbon 12 isotope is referred as AMU here. See, AMU introduced to relate atomic masses. Atomic mass unit introduced to relate all other masses of atoms. Meaning, for example, if I consider oxygen atomic mass, for example, if I consider oxygen, if it has 16 AMU, oxygen if I refer it as 16 AMU, so what is indicating? What it is indicating here? 16 AMU meaning oxygen atom is 16 times heavier than 16 times heavier than AMU. Remember, AMU meaning atomic mass unit, which is used to relate all other atomic masses, which is equal to 1/12 of mass of an atom of carbon 12 isotope. For example, oxygen 16 AMU meaning oxygen atom is 16 times heavier than AMU value. We are going to use in different terms now AMU. Let us see. Further, if I move, gram atomic mass, in short we can refer it as GAM. We can refer it as gram atomic mass. So what is gram atomic mass? Gram atomic mass is, it is equal to mass of 1 mole atoms. Just now we studied 1 mole meaning 6.022 into 10 power 23 atoms. Or I can write here it is equal to mass of 6.022 into 10 power 23 atoms. Anyway, you can define GAM, that is gram atomic mass, is equal to mass of 1 mole atoms or mass of 6.022 into 10 power 23 atoms. See here GAM expressed in grams. Name itself indicating expressed in grams. We'll see overall comparison, we'll see after completion of few more terms. First I am giving just basic definitions of each and every term, and overall in upcoming 5 to 10 minutes we are going to see the important difference between all these terms. If I write simply atomic mass, the term atomic mass meaning here, it is equal to mass of one single atom. Mass of one single atom expressed in AMU. It is expressed in AMU. How? We'll see now. For example, if atomic mass of oxygen, if you want to specify, we mention it as 16 AMU, or you can write U. Atomic mass of oxygen is 16 AMU, meaning oxygen 1 atom mass is 16 times heavier than AMU value. I am repeating, atomic mass of oxygen is 16 AMU, meaning oxygen atom is 16 times heavier than AMU value, or you can mention U. U refers to unified mass. The difference between atomic mass and gram atomic mass: atomic mass is the mass of single atom of the element. Gram atomic mass is mass of 1 mole atoms of the given element. Similarly, if we join for molecular mass, here molecular mass, it is equal to mass of 1 molecule, again expressed in AMU. For example, molecular mass of O2 is equal to, here we mention 32 AMU. Molecular mass of O2 is equal to 32 AMU. And then gram molecular mass. Gram molecular mass, if I specify like this, in gram molecular mass, it is equal to mass of 1 mole. Clearly observe it here, mass of 1 mole of O2 molecules. Mass of 1 mole molecules. Here most important, what you need to focus here, gram atomic mass expressed in grams. Gram atomic mass expressed in grams. Atomic mass expressed in AMU. Whereas molecular mass, even it is expressed in AMU. Gram molecular mass expressed in grams. Most important key terms where students generally make mistakes. Gram molecular mass expressed in grams, molecular mass expressed in AMU, atomic mass expressed in AMU, gram atomic mass expressed in grams. Now, let us take one example to clearly understand the given terms. Observe it. Let us take one question here. What is the atomic mass? Atomic mass of nitrogen, and then gram atomic mass of nitrogen, molecular mass of nitrogen, and gram molecular mass of N2. These 4 questions, if you observe it: gram molecular mass, atomic mass, gram atomic mass. So answer here, atomic mass of nitrogen, we know nitrogen, it is 14 AMU. Gram atomic mass of nitrogen, observe these representations, 14 grams. Molecular mass of N2, double, 28 AMU. Gram molecular mass of N2, 28 grams. See the difference here, atomic mass of nitrogen, gram atomic mass of nitrogen, molecular mass of N2, gram molecular mass of N2. Whenever molecular mass we take N2 molecules, atomic mass we take nitrogen atoms. So most important difference between atomic mass, gram atomic mass, molecular mass and gram molecular mass. Next, moving further, after understanding these terms, let us move further with same. So here we completed 9 terms and move further. Next, 10th important term. Here commonly we use STP and NTP. STP and NTP. So what is the difference between STP and NTP? See here. STP meaning, here we represent First of all, standard, temperature and pressure. NTP meaning normal temperature and pressure. These two terms should be very clear to each and everyone because upcoming numericals based on these two. However, we consider almost these two as synonyms, common. Standard temperature and pressure for STP. Here we take pressure is equal to 1 bar, temperature is equal to almost, that is 273 Kelvin, 1 bar and 273 Kelvin. For normal temperature and pressure, here pressure is equal to, here we take it as 1 atm and temperature is equal to 273 Kelvin. See, temperature as it is, exactly same temperature, but pressure there is difference, like 1 bar here we used, there 1 atm. However, remember here 1 atm is almost equal to 1.013 bar. So that's why here we consider NTP almost equal to STP. Whether in question, whether it mentioned as NTP or STP, we take same conditions like NTP almost equal to STP. Both are same. We consider both as same. So here you remember one important statement. 1 mole of any gas, 1 mole of any gas at STP occupy 22.4 liters. 1 mole of any gas at STP occupy 22.4 liters. Most important statement, remember 22.4 liters, because in upcoming questions we are going to use these values. I am repeating, 1 mole of any gas at STP or NTP, we consider both as same. At STP or NTP occupy 22.4 liters. Keep in mind, both we refer it as same. Questions will be discussed later after completion of important terms in this particular chapter. Next, moving further, next important term, average molar mass. Average molar mass. So what is average molar mass? See, it is mainly calculated for mixture of gases. Used for mixture of gases like O2, N2, H2. If any mixture of gas is given, if they ask to calculate average molar mass, then what we do here? Average molar mass here, MAV is equal to total weight given, that is total weight of all the gases, and then N total, total moles. Total weight, total moles. So how we calculate total weight? W2, W3 by, and goes on based on number of gases. Here moles of gas 1, moles of gas 2, moles of gas 3, and goes on for average molar mass. So we use this formula to calculate average molar mass. Further expansion of the formula will be discussed after completion of few more topics. Okay, and most important commonly used formula here, number of moles which is represented by small n is equal to given weight by atomic weight or molecular weight. Atomic weight or molecular weight. So remember this statement, number of moles is equal to given weight by atomic weight or molecular weight. We'll use this formula in upcoming numericals, plus extra advanced topics will be discussed after completion of few more topics, few more lectures. So number of moles small n is equal to given weight by atomic weight or molecular weight. That is about average molar mass. Next, similarly, How we calculate average atomic mass? When there is mixture, then we calculate average molar mass. Average atomic mass, there is one more term which is average atomic mass. So average atomic mass, when we use average atomic mass, used for isotopes. It is used for isotopes. So for example, if any element having more than one isotope, if they provide information of isotopes, by using information of isotopes, you can calculate average atomic mass. How? For example, if I represent average atomic mass as A bar, think that here A bar is equal to, so here you can specify percentage of or percentage abundance of isotope 1, assume that 2 isotopes available for the given element, into its atomic mass, plus same we refer for isotope 2 into atomic mass of isotope 2 by total abundance. So here keep in mind, average atomic mass, how we calculate, mainly used for isotopes, represented by A bar. Assume that 2 isotopes available for a given element. So percentage abundance of isotope 1 into atomic mass of 1 plus percentage abundance of isotope 2 plus atomic mass of isotope 2 by total abundance. If percentage abundance given in percentage, then total abundance automatically equal to 100 in every case. Next, moving further. Don't worry about calculations. Every question will be discussed in detail in upcoming lectures. Then, density. So, density we know it is mass per unit volume, general definition. But here different densities available, like relative density. So, relative density, if you represent by using RD, so here RD is equal to, relative density is equal to, how we specify? Density of the given gas by density of reference gas. Once again see, normal density mass per unit volume, but relative density here, RD representation, density of the given gas by density of reference gas. Reference gas may be any other gas. For example, for understanding, I am taking one simple question here. For understanding, we get relative density, new term. Calculate relative density of SO3 gas with respect to CH4 gas. Simple question. Calculate relative density of SO3 gas with respect to CH4 gas. So how we calculate? RD of SO3 is equal to density of the gas. Here we know density information not given, but density directly proportional to molecular mass or molar mass. Density directly proportional to molar mass. So here I can use relative density is equal to molar mass of the gas by molar mass of reference gas. If density information given, you can use density formula. If nothing given, you can use molar mass. But remember, 99% of the times they asked question only based on molar mass, relative density. So relative density of SO3 is equal to molar mass of SO3 gas. How much? It is 80 by CH4, it is 16. So overall it is 5. And remember, it is unitless, purely relative density, unitless. That is about relative density. Absolute density like mass per unit volume. Relative density with respect to any other reference gas given in the question, we change it. Then another term, that is vapor density. See, vapor density also a kind of relative term, but it is fixed. Reference gas here always hydrogen. So vapor density here we define like this: density of gas by density of H2, hydrogen gas, or you can write molar mass of given gas by molar mass of H2. And we know molar mass of H2 is equal to 2. So you can change formula. Molar mass of H2 is 2. So you can change formula into vapor density is equal to molar mass of gas by 2. Simple question for understanding the vapor density concept. The vapor density of CO2 is dash. So how we calculate? Vapor density of CO2 is molar mass of CO2, which is 44, by, here we know molecular mass of H2 is 2, so here it is 22. Remember, it is unitless because relative density. Here answer for the vapor density of hydrogen means with respect to hydrogen only we give vapor density. CO2 vapor density, that is 22, unitless. Next term, that is specific gravity. Specific gravity, where most of the students make mistake here. Specific gravity, in short, if I represent like SG, specific gravity. So specific gravity we represent like density of solution. Density of solution by, so density of solution by density of H2O at 4 degrees Celsius. So how we represent? For example, density of solution, here we represent for solutions, this one. Above 2 we represent for gases. Density of water at 4 degrees Celsius, we know it is 1 gram per ml. So then specific gravity exactly equal to density of solution only. Density of solution but without any units. Without any unit, because 1 gram per ml units cancelled here, without any units. Here student make mistakes, you should not do. For example, for understanding, density of, for example, solution is, normal solution is 5 gram per ml. If it is, then specific gravity of solution is 5. Remember, it is unitless. These are very simple things, basic points, but if no clarity about it, chance of making mistakes in mole concept questions. Looks like simple things, but if no clarity, if there is heavy confusion in these topics, very difficult to solve mole concept questions. That's why most of the students face difficulty in mole concept. You will be confident, comfortable after completion of this video based on important terms. Next term, here you can consider, that is molecular formula, empirical formula. Molecular formula, empirical formula. So molecular formula, in short, if we represent like by using MF, empirical formula EF. I am taking directly one example here. If I take benzene, most familiar compound, benzene, C6H6. See, molecular formula represents exact number of atoms of each element. For example, C6H6 benzene formula, where 6 carbon atoms present, 6 hydrogen atoms present. Exact number of atoms represented by molecular formula, whereas empirical formula gives the simplified version. How we can, for example, 6:6, if we simplify it, here you will get 1:1. So here empirical formula of benzene is CH. I am taking another example where C2H4, we know it is ethene. So 2:4, if we simplify it, here you will get CH2. That is empirical formula. C6H12O6. So if you simplify all terms, see, all terms we should find common factor, not only 2. Every term we should find common factor to simplify, not only 2. Here you will get CH2O. Next, if I take sucrose, you take example C2, before going to that, ethane. Ethane, if you observe it, 2:6, if you simplify it, here you will get CH3. So ethane formula C2H6. Now you take here sucrose, C12H22O11. Any chance of simplification here? Any 2 you can do, but not 3. There should be common factor in all the 3 given elements. So here any 2 you can simplify, but others remain constant. That's why you cannot simplify here. As it is, we write C12H22O11. So one more molecular formula, empirical formula concept. Simplest representation is empirical formula. Exact representation is molecular formula. Next, percentage composition. Percentage composition of elements in a given compound. In a given compound. So how we calculate here? I am taking one example here, C2H6, which is ethane. So how we calculate here? Percentage calculation, see. For example, the percentage of carbon here is equal to what we do? So mass of carbon in the given compound by total mass of compound. Total mass of compound into 100. Simple, like normal calculation how we calculate. But mass of carbon, not atomic mass. The total mass of carbon in the given compound. So mass of carbon 2 into 24, 2 into 12, 24. Total mass of compound 24 carbon plus 6 hydrogens into 100. So overall here what we are going to get? 24 by 30 into 100. Calculate percentage, everyone. Next, similarly, once if we know percentage of carbon, hydrogen, how we can do? 100 minus percentage of carbon. But method I am showing how to calculate here. Here mass of carbon into 2 we do. Here similarly mass of hydrogen into 6 by total mass of compound, entire compound whatever given here, into 100. So if you substitute here mass of hydrogen, how much? 1. So overall 6 by 30 into 100. So overall if you do calculation for this, overall percentages you can get value. So here how much you will get? So here 20%. If it is 20%, here automatically 80%. 20% as well as 80%. Once again, everyone observe clearly here how we did calculation. For the calculation of percentage of carbon in the given compound, that is C2H6. Overall here compound is 30 molecular mass, and each element masses we used here. Observe it. If any doubt, once again revisit this particular page. So molecular formula, empirical formula concept also we completed. vapor density, relative density, nothing but relative density here, done. Next, moving to Gay-Lussac's law. Gay-Lussac's law here, at constant temperature and pressure, at constant temperature and pressure, in simplest way I am writing here, not exact statement, simplest for understanding purpose, gases combine in simple ratio by volume. At constant temperature and pressure, gases combine in simple ratio by volume. For example, if I take one equation like, see, it is valid only for gaseous chemical reactions. I am taking here balanced equation which is forming 2NH3, all are in gaseous form. So here 1 volume of nitrogen according to stoichiometric coefficient combining with 3 volumes of hydrogen to form 2 volumes of ammonia. 3 volumes of hydrogen forming 2 volumes of ammonia. So now if we consider ratio by volume or volume ratio, it is simple whole number ratio. Every time you get a simple whole number ratio 1:3:2. Simple ratio by volume according to Gay-Lussac's law of combining volumes. Simple equation where gas is combining and the ratio by volume always simple ratio according to statement. Then Avogadro's law. Next statement. So according to Avogadro's law, at constant temperature and pressure, volume directly proportional to number of molecules, which is directly proportional to number of moles. At constant temperature and pressure, volume directly proportional to number of molecules. As we know, 1 mole of substance contains 6.022 into 10 power 23 molecules. 2 moles contains 2 into 6.022 into 10 power 23 molecules. More, if moles increases, number of molecules also increases. That's why volume directly proportional to number of molecules, which is directly proportional to number of moles. So if volume increases, number of molecules and number of moles automatically increases. That's what overall conclusion of this statement under given Avogadro's law. Next, few more terms like isobars. Isobars, these are atoms of different elements having same mass number but different atomic number. Isobars. Examples, argon as well as calcium if I take, both are having same mass number but atomic number is different. Such substances are referred as isobars. And then similarly, isotones. Isotones, these are having same number of neutrons. How we calculate neutrons? For example, see here. Magnesium molecular mass, that is atomic mass 24, atomic number 12. 24 and 12. Similarly, sodium atomic mass 23, atomic mass they provide in exam, no need to remember, 11. So here number of neutron calculation, how we do? Number of neutrons is equal to mass number minus atomic number. Superscript is mass number, subscript is atomic number. 24 minus 12, that is 12 neutrons. Similarly here, in case of sodium, here you will get 23 minus 11, so 12 neutrons. So both are isotonic pairs. You can say both are in isotonic relation. Next, isodiaphers. Isodiaphers having same A minus 2Z value. A minus 2Z value, remember it is Z or Z, here it is 2. A minus 2Z value. Otherwise, how we can mention? Having same N minus P value. What is N here? N is number of neutrons, P is number of protons. So, elements with same A minus 2Z value or same N minus P value comes under isodiapheric pairs. With one example, you will get more clarity here. Potassium 39 and 19, fluorine 19, 9 atomic numbers. So here, if I use the relation A minus 2Z, 39 minus 2 into 19, which is equal to 1. Similarly for this, 19 minus, you take here 19 minus 2 into 9, which is equal to 1. So both are having same N minus P value or A minus 2Z value, then both are referred as isodiaphers. And then next term, isosters. Isosters, these are having same number of atoms, plus same number of electrons. Same number of atoms and then same number of electrons. Example for such compounds. Think everyone. Example for isosters, where same number of, you can write clearly, same number of atoms plus same number of electrons. Together both should be satisfied. For example, let us check whether it is valid or not. I am taking a CO2 and N2O. CO2 and N2O. Let us check now whether verify it. How many atoms here? 3 here, 3 here. So number of electrons, how many? Carbon 6 electrons, oxygen, each oxygen 8 electrons, overall 2 into 8, 16 plus 6, 22 electrons. Here 2 into 7, 14 plus 8, so overall here also we are getting 22 electrons. See, both are satisfying, both are having same number of atoms, same number of electrons. Hence, such type of pairs are referred as isosteric pairs. Next term, isoelectronic species. So isoelectronic species, how we define? Having same number of electrons. For example, mostly we refer it for ions, same number of electrons. See, even here isosteric pairs having same number of electrons. But here isosteric pair, same number of electrons as well as atoms should be same. But here same number of electrons should be present. For example, Na plus Mg plus 2. Number of electrons, if I observe it, here Na plus, sodium having 11 electrons, but Na plus meaning loss of 1 electron, 10 electrons. Mg plus 2 having 12, Mg having 12 electrons, Mg plus 2 means loss of 2 electrons, 10 electrons. Both are having same number of electrons. Hence, these are isoelectronic species. So remember, these are most important terms which we should focus more before going to numericals. See one quick recap here. In today's lecture, we completely focused on lowest possible basics where students make mistakes: atomic number, mass number, isotopes, mole, AMU, GAM, atomic mass, molecular mass, gram molecular mass, respect to difference, STP, NTP, where maximum chance of confusion, average molar mass, average atomic mass, density, relative density, vapor density, specific gravity, molecular formula, empirical formula, percentage composition, Gay-Lussac's law, Avogadro's law, isobars, isotones, isodiaphers, then finally isosters and isoelectronic species. Every student must go through these important terms before going to further advanced topics. So today's video, only basic terms we discussed. In upcoming video, which is continuation for this, we are going to discuss series of lectures on mole concept, basic to advanced. Once if you go through this series of lectures, you will be confident in writing JEE Mains as well as JEE Advanced. I hope you are going to watch all these lectures in series so that no confusion, with more confidence you can attempt JEE Mains as well as Advanced. Thank you for watching. Thank you for your patient listening.